Dear participants, welcome back after a short break. Professor Tokonami sir will be resuming his lecture again in this second session. So I invite Professor Tokonami sir to again resume his lecture on radon and thoron.
Thank you. Can you hear me? Can you hear me?
Yes, I can hear you.
Okay.
Yeah, hello.
So I will explain about IAEA guidelines, general safety requirements, part 3. As you know, there are 3 exposure situations, namely planned exposure situation, existing exposure situation, and emergency exposure situations. Then we have 3 categories of exposure. That is, they are occupational exposure, medical exposure, and public exposure. This document covers all the situations and all the exposures. ICRP recommendations. The ICRP previously differentiated between practices that increase doses and interventions aimed at reducing them. In its 2007 recommendations, the ICRP adopted a situation-based approach to classify potential radiation exposure scenarios into 3 categories: existing, planned, and emergency exposure situations. It applies a unified set of fundamental protection principles to all these scenarios. Basic safety standards on known as a criteria for the regulation. Exposure to natural sources is normally considered as an existing exposure situation. If the activity concentration of any radionuclide in the uranium or thorium decay chains exceeds 1 becquerel per gram, or potassium-40 exceeds 10 becquerel per gram, apply requirements for planned exposure situations. Okay. Exposure to radon in workplaces. Radon exposure is typically not regulated as a standard practice, but is managed under the guidelines for existing exposure situations. The reference level for radon shall be set at a value that does not exceed an annual average activity concentration of radon of 1,000 becquerel per cubic meter, with account taken of the prevailing social and economic circumstances. Occupational exposure to radon is regulated under the requirements for planned exposure situations in the following cases: when exposure to other radionuclides from the uranium and thorium series is already managed as a planned exposure situation; when, despite the remedial actions, radon concentration remain above the established reference level. A worker's load depends on the type of work, non-activity, time, and protective measures. It is crucial that all individuals involved in managing known equipment and waste possess the required competence and awareness of the associated risks, work systems, and control measures. This includes managers, radiation safety officers, safety engineers, technical engineers, supervisors, technicians, and others. Control gamma exposure. Non-material emit gamma radiation and require monitoring. Facility designs ensuring adequate distance, providing shielding with walls, and etc. Workplace practices, developing rules and procedures to manage exposure durations. Safety measures, utilizing warning signs and physical barriers to enhance protection. Control radionuclides in airborne dust. Airborne contamination can occur wherever dry materials are handled or processed. Spills and the spread of materials to other areas usually pose no radiological concern unless the activity concentration are sufficiently high. Dust sampling involves taking a sample of air through a filter medium. Workplace ventilation is often implemented to control dust, which may already be regulated by occupational health and safety standards for non-radiological reasons. For control radon exposures, ventilation, particularly in underground mines, ventilation is crucial. Occupancy time. In case where there are practical limitations on providing sufficient ventilation, occupancy time may need to be managed. Workplaces with high thorium-232 contents. Additional measures may be necessary to control toron. Regarding transport of norm, the guidelines are encapsulated in the IAEA Safety Standard Series, number SSR 6 regulations for the safe transport of radioactive material. Norm is classified as radioactive material. However, not all norm falls under the scope of the transport regulations. The scope of application of the transport regulations to norm depends on activity concentrations and whether or not the radionuclide content is incidental to the use of the material. The purpose of transport regulations for radioactive materials, including natural occurring radioactive material, is to ensure the safe and secure transport of such materials while minimizing risks to human health, property, and the environment. Contaminant of radioactivity, control of external radiation levels, covered all radioactive materials. Not in Japan. Japan is deficient in mineral resources and most mines for various resources except limestone and small number of precious metal. The significant issue on norm regulation would be exposure of workers handling various types of industrial raw materials. The estimated annual effective dose was below 1 millisievert per year, which aligns with the dose criterion outlined in the International BSS Basic Safety Standard for the exemption of bulk materials containing natural radionuclides. However, the annual effective dose exceeded 1 millisievert per year in only the most critical scenario where a worker handled materials with natural radionuclides from the thorium-232 series at concentration exceeding several hundred becquerel per gram. The summary of this lecture: known is present across various industries. Every industry has unique characteristics and specific exposure scenarios. It is crucial to develop a comprehensive understanding of each industry to address norm effectively. Offering professional training courses for workers and employees handling non-contaminated facilities is vital to ensure safety and compliance. So here is the last lecture for my talk. Fukushima nuclear accident. The 2011, we had a big earthquake. See, this was the fourth most powerful earthquake recorded in the world since 1900. The time, 2:46 p.m. on Friday, March 11th, 2011. Epicenter 72 kilometers east of Oshika Peninsula here, of Tohoku region. Magnitude was 9. Duration was 6 minutes. Here's the epicenter. This is Fukushima nuclear power plant. The Tokyo is far from 220 kilometers far from the Fukushima Daiichi nuclear power plant. Here's a photo. A 3-story building collapsed by the earthquakes in Sukagawa City, Fukushima, on March 11. The height of tsunami is more than 10 meters. The place, the Pacific coastline of Japan's northern island. On March 11th, 3:15 p.m., tsunami struck Onahama Port on Iwaki City, Fukushima. Fishing boat and vehicles were carried away. This was the land. Here is a geographical situation of Fukushima Daiichi nuclear power plant. Onagawa was a nuclear power plant closest to the epicenter of the earthquake, but it was not significantly affected by the tsunami, and it was quickly taken to cold shutdown. The one operable reactor at Tokai also reached cold shutdown without any incident. 2 reactors at Fukushima Daini experienced pressure control problems, but eventually all 4 reactors reached cold shutdown. Only Fukushima Daiichi nuclear plants were affected. Unit 3 and Unit 4 at Fukushima Daiichi nuclear power plant were destroyed by a hydrogen explosion and fire. This photo was taken on March 15, 7:30 a.m. See, here's the damage by tsunami at Fukushima Daiichi. Here's the Fukushima Daiichi event sequence. date March 11, 2:40 p.m., the 9.0 magnitude earthquake strikes. Ground acceleration triggers automatic shutdown of all 3 reactors in operation. A 14-meter tsunami triggered by the earthquake disables all AC power to Unit 1, 2, and 3 at 3:42 p.m. At 3:45 p.m., fuel tanks for emergency diesel generators are carried off by the tsunami. At 4:46 p.m., water infection fails in the emergency core cooling systems of Unit 1 and 2. Date March 12. At 9:07 a.m., a pressure relief valve is open on the Unit 1 pressure vessel. 3:36 p.m., a hydrogen explosion damages the structure of the Unit 1 reactor building. At 8:20 p.m., seawater injection to the Unit 1 pressure vessel begins. On March 13, water injection fails in the emergency core cooling system of Unit 3 at 5:58 a.m. At 9:20 p.m., a pressure relief valve is open on the Unit 3 pressure vessel. Water injection fails in the emergency core cooling systems of Unit 1 and Unit 2. Note that events in red letters are closely related to the release of radioactive materials into the environment. On March 14, at 11:01 a.m., hydrogen explosion damages the external structure of the Unit 3 reactor building. The seawater level in the Unit 2 pressure vessel is found to be low, leading operators to conclude that reactor cooling is no longer functional. At 1:25 p.m. At 4:34 p.m., seawater injection into Unit 2 pressure vessel begins. On March 15, an explosive sound is heard at Unit 2, and it concluded to indicate an abnormality in the pressure suppression pool. At the same time, a part of a wall, the operation area, Unit 4, is damaged at 6:20 a.m. At 9:38 a.m., a fire breaks out in the Unit 4 reactor building. The Unit 4 fire is extinguished at 12:29 p.m. On March 16, at 8:37 a.m., a large quantity of white smoke issues from Unit 3 reactor building. On March 17, Self-Defense Force helicopters drops water on the Unit 3 reactor building for the first of 4 times. 9:48 a.m. At 7:05 p.m., a police water cannon truck begins injecting water into the Unit 3 reactor building. Self-defense pumper trucks begin injecting water into the Unit 3 reactor building for the first of 5 times at 7:35 p.m. On March 18, at 10 a.m., it is confirmed that the common spent fuel pool for Fukushima Daiichi is filled with water, and no abnormalities are observed in the spent fuel dry cask storage buildings. This table shows the radioactive materials released from Fukushima Daiichi nuclear power plant. The half-life, decay of type of decay and emitters and radionuclides. Inert gas, krypton and xenon, volatile elements, iodine-131. This is most significant radionuclides for the general public under the emergency situation. And here is a cesium, radioactive cesium, 134, 136, 137. A radioactive material released from the Fukushima Daiichi nuclear power plant. Here is the monitoring data around Fukushima. The unit is microsievert per hour. A large amount of radioactive materials were carried into the northwest direction. Here is the Fukushima Daiichi nuclear power plant, and we found the highest gamma dose rate here, measured on March 20. In Fukushima, it began to rain and snow on March 15 afternoon. Here are time variations of radiation monitoring data in two cities, Fukushima City and Tokyo. On March 15th afternoon, gamma dose rate suddenly increased in Fukushima City. It is considered to be due to rainfall, that is, wet deposition of radioactive materials. Several peaks of the gamma dose rate were found in Tokyo. A radioactive plume passed through the city. When another plume passes through the city, it rained and consequently radioactive materials deposited on the ground. Here is a simple data analysis for radionuclide fractions consisted by ambient gamma dose rate in Fukushima City. We have a data on time variation of ambient gamma dose rate measured in Fukushima City here. Elapsed day, elapsed time, and dose rate. In order to estimate a radionuclide fraction, we need assumptions, several assumptions. The following radionuclides were consisted of by the ambient gamma dose rate: Thorium-132, iodine-131, iodine-132, cesium-134, 136, and 137. For analysis, after considering the half-life of each radionuclide, monitoring data were estimated with potential curve fittings. As a result, about 80% of gamma dose rate observed on March 17, 2011 was estimated to be derived from Thorium-132 and its progeny, iodine-132. This fraction is close to another measurement and analysis with 63%. It's similar. Terrestrial pathways of transfer of radionuclides and dose to humans. Radioactive materials go to the air, and by external exposure, human people receive the dose. By inhalation, the people receive the dose to the body. by deposition, radioactive materials placed on the surface of soil. And by transfer through the crops, here's the diet contaminated with radioactive materials. By ingestion, people take the radioactive materials and eventually receive the dose. Main pathway of internal exposure in Fukushima nuclear accident. Inhalation is higher possibility. Ingestion is lower possibility due to quick countermeasures on foodstuff. Regardless of ages, many people might have taken radioactive materials. When the radionuclides are taken into human bodies, iodine deposits in thyroid. Strontium deposits in bones because its behavior is similar to calcium. When plutonium is inhaled, it deposits in lung and bone. Cesium is soluble to blood and is distributed in the whole body, such as muscle. Some radioactive materials are excreted by metabolism. Here is the biological half-life. Iodine 80 days, cesium 70 to 90 days. In the case of strontium and plutonium, the biological half-lives are much longer than others because they deposit in the bone. On March 13, the Radiation Safety Council at Hirosaki University convened to discuss the policy in response to the nuclear accident. At the request of the Japanese government, the council decided to dispatch our university staff members to Fukushima to assess residents in the area. The first, our team, Hirosaki University team, was sent to Fukushima on March 15. Two important projects are involved, namely screening tests for radioactive contaminations among the general public in Fukushima Prefecture, temporary home visit within the 20 kilometers evacuation zone for displaced residents. Another significant initiative in Fukushima involved fieldwork focused on radiation measurements and sampling to help reconstruct exposure doses. Here is a related article from the local newspaper. This is me. I was saying something in front of our president. As a screening test for radioactive contamination is defined as the presence of radioactivity in unwanted area. Contamination occurs when a radioactive material is deposited on or in an object or a person or a place. GM survey meter was used for the screening test. Contamination means count rate exceeds 100,000 ppm. In this case, decontamination is needed. In the case of partial contamination, count rate is between 13,000 and 100,000 ppm. In this case, decontamination is suggested. No contamination count rate does not exceed 13,000 CPM. In this case, no decontamination is needed. Twenty teams from our university were dispatched to Fukushima until the end of July 2011. Eventually, more than 5,000 people in Fukushima was inspected. Also, in parallel with such activity, we carried out a survey, carbon survey along an expressway. Here is our city, Hirosaki, and here is Fukushima, and Fukushima nuclear power plant. Those rate measurements were made on March 16, April 11, and April 25. Distance from nuclear power plant to measuring point 60 to 355 kilometers. We used a detector of 1-inch sodium iodine scintillation survey meter here. Measurement time is every 1 minute, and also we recorded the location, geographical location, using the global positioning system. Eventually, more than 100 measurement data were obtained. Also, we estimated the shearing effect by car body, 1.9 with 56 data. Also, we made a comparison between pavement and unsealed surfaces. Here is the data result of our carbon survey. Distance from Fukushima nuclear power station and dose rate in air. We started here from Hirosaki to Fukushima. As you can see, after accident, for example, March 16, the ambient dose rate in air increased rapidly as we approached Fukushima very highly. In the first survey, dose rate increased rapidly, 0.08, this is a natural level, to 11 microsievert per hour. The second and third surveys difference dose rate profile along the expressway. Obvious difference is found around Oshu City. Dose rate differs by a factor of 10 between first survey and the second survey. Second is here, green. Before, fortunately, we have the background data on the expressway here. Also, the number data is small. Yeah, this is actual data. The black line represents for the theoretical calculation based on the natural radioactivity concentration from the geological data. Difference data before accident were obtained by 12 years old boy, my son, together with me. He measured gamma dose rate along the expressway in August 2010 with me. This is the first contact of radiation for my son. My son provided data, precious data on the as a background, but we didn't put his name as a co-author. This is a paper based on our survey time variation of dose rate are artificially increased by the Fukushima nuclear crisis. So 2011, June. My son is missing. After 15 years, we have a co-authored paper. My son, he's studying about transparent X-ray shielding solutions. So we, son and I, published a paper, SES omega, very recently. So we measured gamma spectrometry in Fukushima accident. As you can see, this is a very unique alpha gamma energy spectra. We found a lot of gamma peaks. Thorium-132, Iodine-131, Cesium-137, 134, like this. We use a 3 inches sodium iodine scintillation detector. So we examine the fraction of gamma dose rate. You see, this city is located in the northern west. The first plume reached this area. You see, the most significant contribution is iodine-132 produced by thorium-132. But this city is located south of nuclear power plant. The pattern, color pattern is different from 3 areas. The main contributor is iodine-131. That means the different plume reached this city. Also, the components of the other plume is different from the first one. But here is a result on the gamma dose rate at screening venues from March 16 to May 27. Here's outside the outdoors in Fukushima. More than 13 microsievert per hour is not normal. Red one is indoor dose. Indoor dose much smaller than outdoor dose rate. Also, we recorded our personal dose using this device, digital dosimeter. The highest dose is approximately 100 microsievert. I received this dose. I was the highest. Also, we carried out a siloed study. More than 6,000 people evacuated from the coastal areas in Namie Town and State Tsushima District from March 12 to 15, 2011. Yeah. Radioactive plume reached Tsushima District. Actually, radioactive plume passed through like this way, this direction. And the radioactive reached Tsushima district in the afternoon of March 15. We measured the radioactivity, gamma rate, dose rate from iodine 131 using sodium iodine scintillation spectrometer. Measurement period April 12 to 16. The number of measurement 45 evacuees from coastal area and 17 residents. Totally 62 persons are inspected. The range of age 0 to 83 years old. The measurement time is 5 minutes. Here is the result. Thyroid equivalent dose due to iodine intake. The over 20s, 74% were detected. The range LD to 33 millisieverts. Median value is 3.5 millisieverts. For children less than 19 years old, 75% detected. Range LD to 23 millisieverts. Median value is 4.2 millisieverts. This dose was calculated according to iodine 131 activity in thyroid and the age-dependent equivalent thyroid dose coefficient. The thyroid equivalent doses assessed in this study were much smaller than the mean thyroid dose in the Chernobyl accident, namely 490 millisievert in evacuees. Compare these data. This is Chernobyl. Here is Fukushima. Also, we carried out biological sampling and analysis. We measured radioactivity of cesium, radiocesium in urine using germanium detector. The maximum effective dose was estimated to be 0.7 millisievert for adults. Our data were published in scientific reports in 2012. Here. Further studies on thyroid dose. Not only radioiodine but also radiocesium in the body were detected in the survey carried out by us in April 2011. So here was the assumption. The ratio between iodine and cesium will be constant when hell if these radionuclides in the same pool were taken at the same place. But there would be uncertainties here. When did they inhale? How did they take an action? Additional intake of radiocesium through another pathway by ingestion. Personal difference on biological parameters such as biological half-life and thyroid uptake factor. So we carried out thyroid dose survey for public and we obtained the gamma spectrum like this. Here's a iodine 131 peak. Also, we obtained the peaks of cesium, radiocesium. Then, we determined the counting efficiency of the detector for the calculation of radiocesium activity in the body. We obtain the counting efficiency using a phantom. Then use the ratio between iodine 131 and cesium 134 or cesium 137. It is possible to calculate the thyroid dose using radioiodine activity estimated by whole body counters data. Here is the calibration of measurement equipment under the same geometric arrangement. The radioactive materials were filled with the whole body. That's barium, cesium, and quark. Here is the calculation of the whole body retention due to acute inhalation of cesium 134 on March 15. We measured here after 30 days 0.25.2%. The whole body retention by acute inhalation of cesium. So then date of inhalations here 51.2%. The ratio between iodine 131 and cesium 134 was obtained from 5 persons statistically available among 62 persons inspected as geometric mean of 0.23 and maximum of 0.87. Conservatively, we took the highest value, 0.84. So sodium iodine 131 can be obtained by cesium 134 radioactivity concentration using this value. Here is the result. The maximum value is 18 millisievert. Minimal value is 0.9. The median value is 2.7. It's quite similar to our previous study. Thyroid dose was estimated using whole body counter data obtained from July to August 2011. Only 399 persons whose radiocesium activities were statistically detected among 2,393 persons. In this analysis, additional intake due to ingestion was not considered. For dose restructuring, following information available or needed: time variation, ambient dose rate in cities, activity concentration in environmental or biological samples such as soils, plants, milk, water, and urines, activity in the body, radioiodine in the thyroid or urine, radiocesium in the whole body urine. When did radioactive plume pass through cities? Using an air dispersion model, atmospheric activity concentration can be estimated based on the source term analysis. Here are the approaches to initial exposure situations. We have deposition radioactivity just after nuclear accident. If proper air dispersion model is applied, we can obtain the we can estimate atmospheric activity concentrations, but there is a question: how did they deposit on the ground? Dry deposition or wet deposition? Anyway, using the atmospheric activity concentrations, we can get the radiation doses. The ambient dose rate conversion factor for all immersion and ratio of radionuclides, we will have concentration in air. Then, using the conversion factor for internal dose and exposure period, we will get the internal dose. This figure shows a typical time variation of ambient dose rate without wet deposition. This area derived from the dose due to airborne radioactivity. So we try dose estimation using ambient dose rate. Yeah. Dose rate due to air immersion in Iwaki and Fukushima respectively were measured in 1 week after the accident. Eventually, E-head was assumed during this period 9 hours, and when a radioactive plume due to the accident was staying. Iodine 131 gives 1.6 millisievert as a committed effective dose. Therium, equivalent to iodine 132, gave 0.1 millisievert. Most contributable fraction is coming from iodine 131. This is also using a soil activity. We calculated the dose. The iodine 131 was the highest. The conclusion: radioactive plumes enhanced radiation levels in several cities. Therium 132 and its progeny iodine 132 was regarded as one of the most dominant radionuclides, enhanced radiation levels under an initial situation. Thyroid dose due to iodine 132 was estimated to be approximately plus 10%. Thyroid doses of radioiodine 131 were estimated to be 20 to 30 millisievert as a maximum value based on our own data. For restructuring the initial dose, every effort is still being made using environmental radiation data, air dispersion modeling, and deposited radioactivity. This is all my talk. Thank you very much for your kind attention.
Thank you very much, sir. So, dear participants, if you have any question, please unmute yourself and you may ask the question.
The participants are also requested that if they have any queries regarding this course or content, regarding any content which has been delivered by either of the speakers, so you could always send us an email also. So now, formally, let me thank Dr. Shinji Tokonami and for giving his very valuable insights. It is indeed a great honor and privilege to stand here today to express my heartfelt gratitude to Dr. Tokonami for his invaluable contributions in this GIAN course on environmental radioactivity. So, Dr. Tokonami, I think your lectures have been nothing short of enlightening the people, or especially the persons who are working as a researcher in the field of environmental radioactivity. And your deep expertise in the environmental radioactivity, your innovative approaches to the research, and your ability to distill complex concepts into clear and comprehensible ideas have inspired us during the tenure of these 4 days and enriched all of us. I also am very thankful to your commitment to advancing knowledge to this critical area of study, so which is really admirable. So though you are engaging different sessions with your busy schedule, so I thank you that you have spared a lot of time for us and delivered your insight and expertise to make the participants understand that what is the basic things which are required to start a basic research in the field of environmental radioactivity, and what are the different things which they should consider for the measurement, especially like today you have mentioned the different activities which Hirosaki University is undergoing, and a lot of efforts which your university and you are putting. So the knowledge and the perspectives you have imparted will surely guide us in our academic pursuit and research endeavors, and of course the practical applications in the field of environmental radioactivity. So I, on behalf of everyone present here, extend my deepest gratitude on the behalf of my institute, on the behalf of my director, on the behalf of Coordinator GIAN, National Coordinator GIAN, to you, so that you have been an integral part of this program. So as we conclude this session, we hope that the connections formed and the knowledge shared will pave the way for the future collaborations and advancements in this critical issue. So I thank you again, and we wish you continued success in all your future endeavors, and look forward for welcoming you in person in near future. So thank you, sir. So nice of you. And I will be sharing some documents with you, which as your feedback we will be requiring for this program. So today is the last session, but tomorrow is the last session for this GIAN program, where we will be giving some test also, some live demo also, and one basic lecture. So thank you, Dr. Tokonami. Thanks for your time. Thanks once again. Jai Hind, India.
Thank you very much. Thank you very much for your kind words. So I'm happy to deliver some lectures. Actually, I spent a lot of time to prepare the many slides. But anyway, so I was happy to be here. And hopefully
in future we will have some physical presence also, and maybe some
near
program.
Hopefully. I will visit India again. Thank you very much.
Thank you.
So have a nice day. Bye. Thank you.
So thank you very much, sir. So once again, on the behalf of NIT Jalandhar and Professor Rohit Mehra, sir, I extend my heartfelt thanks to Professor Shinji Tokonami for his valuable time and effort in making this GIAN course a success. So with this, I conclude this last session of the day 4. And again, a reminder for the participants that there will be a lecture tomorrow at 10 a.m. and after that there will be a demonstration session, and followed by that there will be a quiz on the basis of which certificates will be awarded to all the participants. So make sure that everyone is present and to run the quiz. So,
okay, sir. Thank you.
Thank you very much, sir.
Thank you. Goodbye.